Hello everyone. This video is a book review on the great book Key Points from Software Engineering at Google by Titus Winters, Tom Manshrek, and Hyrum Wright. I'll be covering the key points worthy of mention from each chapter in this awesome book in this video. So let's start with the preface. Here are the key ideas from the preface. Software engineering encompasses not just the act of writing code, but all of the tools and processes an organization uses to build and maintain that code over time. The three fundamental principles that software organizations should keep in mind when designing, architecting, and writing their code are time and change, how code will need to adapt over the length of its life, scale and growth, how an organization will need to adapt as it evolves, trade-offs and costs, how an organization makes decisions based on the lessons of time and change and scale and growth. Google's main aspects of its software engineering landscape are as follows: culture, processes, tools. What this book isn't. This book, it doesn't cover software design. That subject would require its own separate book. Key ideas for Chapter 1. What is software engineering? Software engineering differs from programming in dimensionality. Programming is about producing code. Software engineering extends that to include the maintenance of that code for its useful lifespan. There is a factor of at least 100,000 times between the lifespans of short-lived code and long-lived code. It's silly to assume that the best practices apply universally on both ends of that spectrum. Software is sustainable when, for the expected lifespan of the code, we're capable of responding to changes in dependencies, technology, or product requirements. We may choose not to change things, but we need to be capable. Hyrum's law. With a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. Every task your organization has to do repeatedly should be scalable, linearly or better, in terms of human output. Policies are a wonderful tool for making process scalable. So process inefficiencies and other software development tasks tend to scale up slowly. Be careful about boiled frog problems. Expertise pays off particularly well when combined with economies of scale. Because I said so is a terrible reason to do things. Being data-driven is a good start, but in reality, most decisions are based on a mix of data assumption, precedent, and argument. It's best when objective data makes up the majority of those inputs, but it can rarely be all of them. Being data-driven over time implies the need to change direction when the data changes, or when assumptions are dispelled. Mistakes or revisited plans are inevitable. Key ideas for Chapter 2. How to work well on teams. Be aware of the trade-offs of working in isolation. Acknowledge the amount of time that you and your team spend communicating in interpersonal conflicts. A small investment in understanding personalities and working styles of yourself and others can go a long way towards improving productivity. If you want to work effectively with a large team or a large organization, be aware of your preferred working style and that of others. Key ideas for Chapter 3. Knowledge sharing. Psychological safety is the foundation for fostering a knowledge-sharing environment. Start small. Ask questions and write things down. Make it easy for people to get the help they need from both human experts and documented references. At a systemic level, encourage and reward those who take the time to teach and broaden their expertise beyond just themselves, their team, or their organization. There is no silver bullet. Empowering a knowledge-sharing culture requires a combination of multiple strategies, and the exact mix that works best for your organization will likely change over time. Key ideas for Chapter 4: Engineering for Equity. Bias is the default. Diversity is necessary to design properly for a comprehensive user base. Inclusivity is critical not just for improving the hiring pipeline for underrepresented groups, but to providing a truly supportive work environment for all people. Product velocity must be evaluated against providing a product that is truly useful to all users. It is better to slow down than to release a product that may cause harm to some users. Key ideas for Chapter 5: How to lead a team. Don't manage in the traditional sense. Focus on leadership, influence, and serving your team. Delegate where possible. Don't DIY, do it yourself. Pay particular attention to the focus, direction, and velocity of your team. Key ideas for Chapter 6: Leading at Scale. Always be deciding. Ambiguous problems have no magic answer. They're all about finding the right trade-offs of the moment and iterating. Always be leaving. Your job as a leader is to build an organization that automatically solves a class of ambiguous problems over time without you needing to be present. Always be scaling. Success generates more responsibility over time, and you must proactively manage the scaling of this work in order to protect your scarce resource of personal time, attention, and energy. Key ideas for Chapter 7: Measuring engineering productivity. Before measuring productivity, ask whether the result is actionable, regardless of whether the result is positive or negative. If you can't do anything with the result, it's likely not worth measuring. Select meaningful metrics using the GSM framework. A good metric is a reasonable proxy to the signal you're trying to measure, and it is traceable back to your original goals. Select metrics that cover all parts of productivity, quants. By doing this, you ensure that you aren't improving one aspect of productivity, like developer velocity, at the cost of another, like code quality. Qualitative metrics are metrics too. Consider having a survey mechanism for tracking longitudinal metrics about engineers' beliefs. Qualitative metrics should also align with quantitative metrics. If they do not, it is likely the quantitative metrics are incorrect. Aim to create recommendations that are built into the developer workflow and incentive structures. Even though it is sometimes necessary to recommend additional training or documentation, change is more likely to occur if it is built into the developer's daily habits. Key ideas for Chapter 8: Style guides and rules. Rules and guidance should aim to support resilience to time and scaling. Know the data so that rules can be adjusted. Not everything should be a rule. Consistency is key. Automate enforcement when possible. Key ideas for Chapter 9: Code review. Code review has many benefits, including ensuring code correctness, comprehension, and consistency across a code base. Always check your assumptions to someone else. Optimize for the reader. Provide the opportunity for critical feedback while maintaining professionalism. Code review is important for knowledge sharing throughout an organization. Automation is critical for scaling the process. The code review itself provides a historical record. Key ideas for Chapter 10: Documentation. Documentation is hugely important over time and scale. Documentation changes should leverage the existing developer workflow. Keep documents focused on one purpose. Write for your audience, not for yourself. Key ideas for Chapter 11: Testing overview. Automated testing is foundational to enabling software to change. For tests to scale, they must be automated. A balanced test suite is necessary for maintaining healthy test coverage. If you liked it, you should have put a test on it. Changing the testing culture in organizations take time. Key ideas for Chapter 12, Unit Testing. Strive for unchanging tests. Test via public APIs. Test state, not interactions. Make your test complete and concise. Test behaviors, not methods. Test structure tests to emphasize behaviors. Name tests after the behavior being tested. Don't put logic in tests. Write clear failure messages. Follow damp over dry when sharing code for tests. Key ideas for Chapter 13, Test Doubles. A real implementation should be preferable over a test double. A fake is often the ideal solution if a real implementation can't be used in a test. Overusing of stubbing leads to tests that are unclear and brittle. Interaction testing should be avoided when possible. It leads to tests that are brittle because it exposes implementation details of a system under test. Key ideas for Chapter 14, Larger Testing. Larger tests cover things unit tests cannot. Large tests are composed of a system under test, data, action, and verification. A good design includes a test strategy that identifies risks and larger tests that mitigate them. Extra effort must be made with larger tests to keep them from creating friction in the developer workflow. Key ideas for Chapter 15, Deprecation. Software systems have continuing maintenance costs that should be weighted against the cost of removing them. Removing things is more difficult than building them to begin with because existing users are often using the system beyond its original design. Evolving a system in place is usually cheaper than replacing it with a new one when turndown costs are included. It is difficult to honestly evaluate the costs involved in deciding whether to deprecate. Aside from the direct maintenance costs involved in keeping the old system around, there are ecosystem costs involved in having multiple similar systems to choose between and that may need to interoperate. The old system might implicitly be a drag on feature development for the new. These ecosystem costs are diffuse and difficult to measure. Deprecation and removal costs are often similarly diffuse. Key ideas for Chapter 16, Version Control and Branch Management. Use version control for any software development project larger than toy product with only one developer that will never be updated. There's an inherent scaling problem when there are choices in which version of this should I depend upon. One version rules are surprisingly important for organization efficiency. Removing choices in where to commit or what to depend upon can result in significant simplification. In some languages, you might be able to spend some effort to dodge this with technical approaches like shading, separate compilation, linker hiding, and so on. The work to get those approaches working is entirely lost labor. Your software engineers aren't producing anything, they're just working around technical debts. Previous research, such as DORA, State of DevOps, and Accelerate, has shown that trunk-based development is a predictive factor in high-performing development organizations. Long-lived dev branches are not a good default plan. Use whatever version control system makes sense for you. If your organization wants to prioritize separate repositories for separate projects, it's still probably wise for inter-repository dependencies to be unpinned at head/trunk based. There are an increasing number of VCS and build system faculties that allow you to have both small, fine-grained repositories as well as a consistent virtual head/trunk notion for the whole organization. Key ideas for Chapter 17, Code Search. Helping your developers understand code can be a big boost to engineering productivity. At Google, the key tool for this is Code Search. Code Search has additional value as a basis for other tools and as a central standard place that all documentation and developer tools link to. The huge size of the Google codebase make a custom tool as opposed to, for example, grep or an IDE's indexing necessary. As an interactive tool, code search must be fast, allowing for a question and answer workflow. It is expected to have low latency in every respect: search, browsing, and indexing. It will widely be used only if it is trusted, and will be trusted only if it indexes all code, gives it all results, and gives the desired results first. However, earlier, less powerful versions were both useful and used as long as their limits were understood. Key ideas for Chapter 18: Build systems and build philosophy. A fully featured build system is necessary to keep developers productive as an organization scales. Power and flexibility come at a cost. Restricting the build system appropriately makes it easier on developers. Build systems organized around artifacts tend to scale better and be more reliable than build systems organized around tasks. When defining artifacts and dependencies, it's better to aim for fine-grained modules. Fine-grained modules are better able to take advantage of parallelism and incremental builds. External dependencies should be versioned explicitly under source control. Relying on latest versions is a recipe for disaster and unreproducible builds. Key ideas for Chapter 19: Critique, Google's code review tool. Trust and communication are core to the code review process. A tool can enhance the experience, but it can't replace them. Tight integration with other tools is key to great code review experience. Small workflow optimizations, such as the addition of an explicit attention set, can increase clarity and reduce friction substantially. Key ideas for Chapter 20: Static analysis. Focus on developer happiness. We have invested considerable effort in building feedback channels between static analysis users and static analysis writers in our tools, and aggressively tune analyses to reduce the number of false positives. Make static analysis part of the core developer workflow. The main integration point for static analysis at Google is through code review, where analysis tools provide fixes and involve reviewers. However, we also integrate analysis at additional points, such as via compiler checks, gating code commits in IDEs, and when browsing code. Empower users to contribute. We can scale the work we do in maintaining analysis tools and platforms by leveraging the expertise of domain experts. Developers are continually adding new analyses and checks that make their lives easier and our code base better. Key ideas for Chapter 21: Dependency Management. Prefer source control problems to dependency management problems. If you can get more code from your organization to have better transparency and coordination, those are important simplifications. Adding a dependency isn't free for a software engineering project, and the complexity in establishing an ongoing trust relationship is challenging. Importing dependencies into your organizations needs to be done carefully with an understanding of the ongoing support costs. A dependency is a contract. There is a give and take. Both providers and consumers have some rights and responsibilities in that contract. Providers should be clear about what they're trying to promise over time. SEMVer is a lossy compression shorthand estimate for how risky does a human think this change is. SEMVer is a SAT solver in a package manager that takes those estimates and escalates them to functions as absolutes. This can result in either over-constraint, dependency hell, or under-constraint, versions that should work well together that don't. By comparison, testing and CI provide actual evidence of whether a new set of versions work together. Minimum version update strategies in SEMVer/package management are higher fidelity. This still relies on human beings being able to access incremental version risk accurately, but distinctly improves the chance that the link between API provider and consumer has been tested by an expert. Unit tests, CI, and cheap compute resources have the potential to change our understanding and approach to dependency management. That phase change requires a fundamental change in how the industry considers the problem of dependency management and the responsibilities of providers and consumers both. Providing a dependency isn't free. Throw it over the wall and forget can cost your reputation and become a challenge for compatibility. Supporting it with stability can limit your choices and pessimism internal usage. Supporting without stability can cost goodwill or expose you to risk of important external groups depending on something via Hyrum's law and messing up your no stability plan. Key ideas for Chapter 22: Large-scale changes. A LSC, large-scale change, process makes it possible to rethink the immutability of certain technical decisions. Traditional models of refactoring breaks at large scales. Making LSCs means making a habit of making LSCs. Key ideas for Chapter 23: Continuous integration. A CI system decides what tests to use and when. CI systems become progressively more necessary as your codebase ages and grows in scale. CI should optimize quicker, more reliable tests on pre-submit, slower, less deterministic tests on post-submit. Accessible, actionable feedback allows a CI system to become more efficient. Key ideas for Chapter 24: Continuous delivery. Velocity is a team sport. The optimal workflow for a large team that developers code collaboratively requires modularity of architecture and near continuous integration. Evaluate changes in isolation. Flag guard any features to be able to isolate problems early. Make reality your benchmark. Use a staged rollout to address device diversity and the breadth of the user base. Release qualification in a synthetic environment that isn't similar to the production environment can lead to late surprises. Ship only what gets used. Monitor the cost and value of any feature in the wild to know whether it is still relevant and delivering sufficient user value. Shift left. Enable faster, more data-driven decision-making earlier on all changes through CI and continuous deployment. Faster is safer. Ship early and often and in small batches to reduce the risk of each release and to minimize time to market. Key ideas for Chapter 25: Compute as a service. Scale requires a common infrastructure for running loads in production. A compute solution can provide a standardized, stable abstraction and environment for software. Software needs to be adapted to a distributed managed computed environment. The compute solution for an organization should be chosen thoughtfully to provide appropriate level of abstraction. Conclusion. Thanks for watching this video. If you found it helpful or have any comments that you'd like to make, just let me know in the comment section below. Thanks again for watching my video. I hope you were able to learn some of the software engineering techniques presented in this book. And if you found this video helpful, feel free to like and subscribe to my video and YouTube channel. And thanks again for watching, and I'll see you in the next video.